Continuing with mediated transport systems, what we did before was define mediated transport, which in this context is going to mean moving something across the cell membrane through a carrier, not a channel. And what we talked about last time was facilitated diffusion. And facilitated diffusion was diffusing something through a carrier, meaning that the something, whatever it is, goes from its high concentration to its low concentration, but through a carrier protein. And since it does that, of course, it's subject to saturation, because when the carrier gets full, you can't transport it any more quickly. And now what we're going to do is go to something that's really fundamental to understanding the next set of notes. It's called primary active transport, and with primary active transport, what you're doing is it's still mediated transport, so it's still using a carrier, and here's the one that we're going to learn today. But it's active transport because what I'm doing is I'm not diffusing something, I'm moving it against its concentration gradient. So I'm moving it from low concentration to high concentration, kind of moving it uphill in the concentration gradient thought. And in order to get something to move against its concentration gradient, you're going to need an energy source. And what we are going to use as an energy source is this classical energy source called ATP. It's not the only way that you can do it, but this is the one that we're going to learn. So I'm going to move ions or molecules or whatever against their concentration gradient across the cell membrane. It's kind of moving them uphill. And when you move something uphill, quite often you need to pump it. So what is a pump? In this context, what we are going to be calling a pump is this guy right here. It's a carrier protein plus ATP. That makes it a pump, okay? The net effect of doing this is that you are going to accumulate particles on one side of the cell membrane. So whereas like with diffusion, we said that if you start out with a concentration gradient and you just do diffusion, then what you're going to get over time is basically the concentration gradient is going to be lost. You're going to have this same amount everywhere. So what happens with active transport? Well, with active transport, if you started out with a concentration gradient and you did active transport, depending on how quickly you pumped, you can end up either maintaining the concentration gradient that you had before, or if you pumped it even more quickly, you would get a steeper concentration. So you are working to accumulate particles on one side of the cell membrane. And this requires both the carrier protein and it requires ATP. And the carrier protein is, of course, the pump. The carrier is shape-specific, so it will move things that fit into the shape-specific binding sites that you see here, 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 here. This one's a specific one, and we're going to look at it. And because it's shape-specific, it's subject to regulation by other things, so you can turn pumps on and off, up and down. We're not going to do that with this one. What we are going to do is we're going to look at this really specific type of active transport, primary active transport, that uses the sodium-potassium pump. And you guys learned the sodium-potassium pump in 1610, but it's going to be really important, fundamentally important to understanding the next set of notes when we really start talking about physiology, like with nervous system transmission. So instead of just having you memorize the pump, what I'm going to do is sort of build the setup for the pump and then put the pump in. So let's start doing that. So what we are going to do is we're going to say, okay, we've got this sort of what seems like an oxymoron, because sodium and potassium are constantly trying to diffuse down their electrochemical gradients because they're ions and they're charged. But somehow, despite that, we managed to maintain the concentration gradient for sodium at about 15 sodiums outside for every 1 inside, despite the fact that they constantly want to diffuse down their concentration gradients. And we managed to maintain the potassium concentration gradient at about 30 potassiums inside for every 1 outside. So how does that occur? How do I manage to maintain these concentration gradients despite the fact that they're constantly trying to diffuse? And so that's what we're going to build, but we're going to build it kind of slowly. And if I were you guys, I would get your own piece of paper and build this for yourself, because then there's way less memorization in physiology. So let's talk about this. So instead of starting with the sodium-potassium pump, let's start with some things that are true about a cell and homeostatic. So we are going to call this the intracellular fluid and this the extracellular fluid. No big deal there. Oops. Hold on just a second. And intracellular fluid and extracellular fluid. In the intracellular fluid, let's talk about some things that are homeostatic and true for the cells. So what tends to be true for the intracellular fluid is that there is a relatively high concentration of potassium and a relatively low concentration of sodium. Okay, that's homeostatic for the cell. Whereas with the extracellular fluid, the opposite is true. There is a relatively high concentration of sodium in the ECF and a relatively low concentration of potassium. And since your notes said it, let's go ahead and identify what we mean by high and low. If I compare the amount of potassium inside to the amount of potassium outside, the ratio is about 30 inside to every 1 outside. And if I do the same thing for sodium, the ratio is about 15 sodiums outside for every 1 sodium inside. Okay, so we've got concentration gradient. Later on, I'll tell you about the electrical nature of the cell and we can add in the electrical gradient. But for right now, let's just focus on concentration gradients. Now, a couple of logic questions for you. First, will sodium or potassium diffuse across the cell membrane in the absence of channels or carriers? So, can it diffuse? For instance, sodium would love to diffuse inside because of its concentration gradient, but it can't. Who remembers why sodium can't diffuse in? Sodium cannot diffuse in because it is a charged or polar molecule, and it tends to be highly hydrophilic and lipophobic, and of course the cell membrane is mostly made of lipids. So what I'm saying here is in this picture is if you do not put in a channel or a carrier, then those things are not going to go anywhere. So let's go ahead and put in a couple of channels. Remember that channels are big enough for sodium and potassium to diffuse through. Okay, so let's call this a sodium leak channel. Okay, and then let's put in one for potassium. Let's call this one a potassium leak channel. Okay, and we're still not talking about the sodium-potassium pump yet. We're just going to show you the reason for it first. So, question for you. Now that I have these channels in, which direction will sodium diffuse when given the opportunity? Okay, so sodium is going to diffuse, what do you think, inside the cell or outside the cell? Let's think about it. So, and then also think about why your answer is what it is. So sodium is going to diffuse, what do you think? It's going to diffuse inside the cell when given the opportunity. And why? Why is it going to diffuse inside the cell? For right now, let's just say, oh, okay, it's got a concentration gradient of 15 to 1. So it's high on the outside and low on the inside. It's going to diffuse in. Okay, same question to ask for potassium. Which direction is potassium going to move when given the opportunity? Potassium is going to diffuse which direction? What do you think? It's going to move, what do you think? So it's 30 on the inside to 1 on the outside. So when given the opportunity, potassium is going to diffuse outside the cell. okay, because of that concentration gradient, because of 30 to 1. I'll add some details about electrochemical gradients later. Okay, so now what we see is that we have created a bit of an issue. So we said that these things were homeostatic for the cell, but it's going to be hard to maintain them because of this and this. Now, those of you who are very logical are going to say, well, why the hell don't you just close those channels? You can't, they're leak channels. So we'll figure out why they exist a little bit later. So just trust me for a minute that they need to be there, but they do cause problems. So how are you going to maintain the homeostatic concentrations in yellow despite these constantly leaking leak channels? And the answer here is the star of the show that we've been trying to get to, and that is our friend, the sodium-potassium pump. So what the sodium-potassium pump is going to do is it's going to be able to maintain the homeostatic concentrations for sodium and potassium that we said were ideal. So let's put it in, and then we'll look at it in the picture from your textbook, and then I'll also show you an animation. But I want you to understand what it's going to do. So the sodium-potassium pump is going to pump ions against their concentration gradient in order to maintain homeostasis. So with this in mind, I don't want to tell you, I want you to tell me, which direction is it going to pump sodium to maintain homeostasis? Okay. So this is what I want for sodium right here, 15 to 1, but this is what I'm working against, sodium constantly diffusing inside. So I am going to pump sodium which direction? I'm going to pump sodium back out, okay? And which direction am I going to pump potassium? Well, potassium, this is what I want, high, inside, low, outside, but this is what's constantly happening. It's diffusing in. So I am going to, I'm sorry, it's diffusing out. I am going to pump potassium back in, okay? But in order to get those ions to move against their concentration gradients, what I need is I need to use ATP. When I use ATP, it becomes ADP. Okay, I pop a phosphate off. So let's hold on to this for just a second. So what I want you to understand is that you don't have to memorize this if you start by memorizing these concentrations, right? And then you're going to know that what the leak channels would do, and then you don't have to memorize what the sodium-potassium pump does because it's logical what it does. Okay, so let me just tell you one more thing and then we will move to the image and the animation. So as far as the amounts of things that are pumped by the sodium-potassium pump, if you call it the sodium-potassium pump, meaning you say sodium before potassium before pump, here's a little trick. Call it the 3-2-1 sodium-potassium pump because it pumps 3 sodiums, 2 potassiums, and uses 1 ATP for the pump every time it runs. So let us now look at the image in your textbook, and then we will also look at the animation. Okay, so here's what the sodium-potassium pump is going to do. It is a pump, meaning a carrier that also uses ATP, and it has 3 binding sites, 1, 2, 3 for sodium, right? These 2 binding sites, I'm fairly certain you could figure out that those are for potassium. And then it uses 1 ATP for the pump. So here's what happens. Once the 3 sodiums bind and the ATP binds, you will hydrolyze a phosphate off of ATP to make it into ADP. The phosphate stays stuck on the protein right here, just like it is. Okay. And that is what you're going to use for energy to get sodium to go against its concentration gradient. Okay, you're going to dump it into the extracellular fluids. It's sodium out through the pump. And when you do that, you're going to reveal 2 binding sites for potassium. When potassium binds, the phosphate's going to fall off, which will change the conformation so that you actually move potassium back toward the intracellular fluid and dump potassium on the inside. So it's the sodium-potassium pump. Now let's look at an animation that shows you the same thing. Ready?
Is an example of an active transport. The sodium-potassium exchange pump is an example of an active transport process. Active transport processes can move substances against a concentration gradient, and they require energy expenditure in the form of the breakdown of ATP. The sodium-potassium exchange pump moves sodium ions out of the cell and potassium ions into the cell.
Okay, now I will narrate the rest of it for you. So now you're looking at this carrier protein. I bet you can figure out what these three are for. Those are for sodium, which is represented here as this pink ball. And the two right here, those are for potassium. And then the one is for ATP. Phosphate binds, use that energy to push the sodium toward the extracellular fluid. At the same time, that reveals the binding site for potassium. Potassium is going to bind. There it goes. The phosphate is going to fall off. And that is going to be the motivator for getting potassium back to the inside of the cell. Okay. So what this pump will do if you run it relatively constantly is, despite those leak channels leaking in, it is going to maintain those sodium and potassium concentration gradients that you needed. Okay, and so in your notes right here, there is a place for the sodium ion channel. It's a leak channel, potassium, and then the sodium potassium pump. What you should do is use arrows and color coding to show you which direction sodium and potassium goes through each of these things. Okay, so how important is this? The sodium potassium pump is in every single cell that you have. And for many cells, the sodium potassium pump maintaining these sodium and potassium concentration gradients uses up about 40 to 60% of all of the ATP that is used by a cell, just running those sodium potassium pumps. If you have cells like nervous and muscular cells that mess with the sodium and potassium concentrations on purpose, then you just need to use the pump more. Okay, so the pump will basically maintain your sodium and potassium concentration gradients. And it also does this thing called maintaining the transmembrane potential. So I'm going to try to explain this to you just once now. And if you don't get it now, it's okay, because I also do it in the next set of notes. But if you can get it now, you'll be a little bit ahead. So what we're going to do is we are going to, one more time, just quickly build this thing, and then just stick with me. This is called the transmembrane potential. So I'm going to draw it all in the same color this time, and we'll do it relatively quickly. So here we go. We've got the ICF and the ECF, and hopefully you can do it with me. The ECF has a high concentration of sodium, low concentration of potassium. The ICF is the opposite, low concentration of sodium, high concentration of potassium, all positive charges. Okay, we said nothing will diffuse unless you add in channels, so let's add them in. And this one's going to be a sodium channel, and this one's going to be a potassium channel. And then you guys said that you understood, well, you didn't say anything, but in my mind you said that you understood that sodium would diffuse in because of its concentration gradient, and potassium would diffuse out because of its concentration gradient. Let's put the numbers in here. So remember, the ratio of sodium outside to inside was 15 to 1, and the ratio of potassium inside to outside was 30 to 1. Okay, so question for you. Let's see if we can get this. So they have different concentration gradients initially. So which one do you think will initially diffuse more quickly, sodium or potassium? And you know that concentration gradient is relative to the transport rate, or the net flux rate. So what do you think? Will sodium or potassium initially diffuse faster? It is actually potassium that initially diffuses faster because of this 30 to 1 concentration gradient. So again, if you don't get this time, it's totally fine. If I started out with a neutral ICF and a neutral ECF, electrically neutral, I had no charge, okay? And then I let this positive ion diffuse out more quickly than the negative ion, or than the other positive ion diffused in. What would happen is, if you give it a minute, you'll get a slight positive charge on the outside, because I started out neutral, neutral, but I diffused positives out slightly faster than I diffused positives in. And then on the inside, you will actually end up with a slight negative charge, because I started out neutral, but there are negatives in there. Okay. And then what I have is I have set up the potential that any charged ion will want to move across the cell membrane. We call it the transmembrane potential. So hopefully it will make sense to you just briefly that because of this charge that I just made right here, positive ions will be attracted to the inside of the cell and negative ions will be attracted to the outside of the cell, because initially the sodium and potassium did not diffuse at the same rate. If this doesn't make sense, it's fine, because we will actually go over it again in the next set of notes. But if it does, that's great too. So the pump, because the pump is constantly maintaining the concentration gradients, and then the concentration gradients mean unequal leaking, the pump sets up what's called the transmembrane potential. And the transmembrane potential is exactly what it sounds like. It's the potential for ions to move transmembrane, across the membrane. So the outside of the membrane is slightly positive with a high sodium concentration, and the inside of the membrane is slightly negative with a high potassium concentration. And the potential exists that now any ion can be motivated to move across the cell membrane. And then once we get to that point, by the way, once we get to this, let's say that not only is this homeostatic and this homeostatic, but now maintaining this difference of charge on the two sides, that's homeostatic as well. And we will see how important it is in the next set of notes. If you didn't get how you got the charge, it's okay. We will both probably be able to talk about it in person, rebuild it for you in person, or I'm going to go through it in the next set of notes as well. Okay, so that is the sodium-potassium pump and primary active transport. Next, we will do secondary active.